Okay, time for the main event. Let's actually talk about binomial distributions. So what we explored in the previous video was a model for prevalence that actually we can apply much more generally than even just prevalence. We're going to be able to model this with any random process that has the following characteristics. And we'll have to start with defining what we call a Bernoulli trial, which is an experiment that has only two outcomes. And we denote the probability of success, which is one of the outcomes, and the other one is failure. So we have two outcomes. So success and failure. And the probability of success is lowercase p. And the probability of failure is 1 minus p. Okay? Bernoulli trials are among the most basic probabilistic ideas where we're talking about something that's binary. So fundamentally, think about a binary variable. So that could be true or false, yes or no, heads or tails, listens to podcasts and doesn't listen to podcasts. Anything that can be answered in a binary by a binary variable is going to be a Bernoulli trial as long as it's random. So in these specific examples that I'm giving here, it's possible that the probability of success and the probability of failure are equally likely. So for instance, if we're talking about flipping a coin, we can maybe call heads the success, and the probability of success is half, and tails is going to be our failure. And success and failure don't necessarily mean that these are good and bad things. We just mean one of them is what we're interested in and the other one is not. Or, for instance, let's say you randomly guess on a multiple choice question with 4 options. Only one of them is correct, right? So then you can either guess correctly, which is a success, and the probability of that would be 1 out of 4, so 0.25. Now, incorrect is more likely because the probability of that then would be 0.75. And we're going to assume that you really are just really randomly guessing, no even reading the question, you just pick one at random. So that's a Bernoulli trial. And in our example that we had, our guiding example, we were looking at each individual person and whether they had hypertension or not. And so what we were actually setting up here was p and 1 minus p, where p was 0.332 and 1 minus p was 0.668. And so our probability of success here is the 33.2%, and the probability of failure is the 66.8%. But again, keep in mind, success and failure are not good and bad. So we're not using a binary that is moralistic. It's not. All it's saying is, what are we interested in? Specifically this event, in which the randomly selected person has hypertension, and the one that we're not interested in is when they don't have it. So now we're here at our main event, which is that a binomial distribution with parameters n being the number of trials, where there's n Bernoulli trials, and p is the probability of success in each Bernoulli trial, which has to be the same across the board. And it comes from n identical and independent Bernoulli trials. So in terms of our example that we were looking at for hypertension, so the prevalence of hypertension, since we had our sample size n equals 6, so our sample size becomes the number of trials, and p being the prevalence rate for each person is our probability of success. Every binomial distribution has to be determined by these two parameters. So we need both of them to determine the distribution of the full distribution. And we have a few key conditions that need to be met in order for this distribution to be the correct model. So first, n, the number of trials, has to be fixed. So we're not pulling in extra people into our sample at any point when we're measuring or doing anything with this random variable. We have taken a sample, done. Or we have a fixed number of trials, we're flipping a coin 10 times and no more. 2, each Bernoulli trial has to have the same probability of success. That can't change throughout. So each person that we've taken in our sample has the same prevalence because they come from the same population. Lastly, the n trials have to be independent. So what happens for one person having hypertension doesn't affect the next person having hypertension, or the likelihood of that, and repeated under identical conditions. This is connected to what we said about each person being selected from the same population, because we want the random selection to be identical. So binomial distributions then, if we're setting up the specifics of this variable, so x, and we're gonna say it's distributed as binomial, and sometimes we'll use this notation, we'll just write binomial and then parentheses n comma p, which just means this has the binomial distribution with parameters n and p. Then that support is the set 0, 1, 2, all the way up to n. And so there's n plus 1 possibilities, possible outcomes. So none, 1, 2, or all of them are successes. Discrete, so you can't have like 0.5 successes. You only count in whole numbers. And the probability mass function, and connect this to what we did in the previous video, is going to be from our n trials, select x of them. Again, x is a whole number, so 2, 5. Any whole number less than n but positive, times p raised to the x power representing the x successes that have occurred times 1 minus p raised to the n minus x power. So to be clear again, so this is a combination. So this accounts for the combinations of x trials out of n of them. This accounts for the probability of those x successes. And this factor accounts for the probability of the n minus x successes. And what all that means is if there's n total, right? So for instance, in our specific example that we had before, we had something along the lines of 6 choose x times 0.332 x times 0.668 n minus x. And for the specific value of x, like maybe the probability that exactly one person has this, that has hypertension, then out of 6 of them, we choose 1 times our one success is the probability 0.332 raised to the 1 power. And then all the rest of them are failures. So that's 0.668 raised to the 5th power. And that represents the probability of exactly one of them being successful. And so we can now make some inferences and learn some things about the distributions of these Bernoulli trials. So as an example, let's say we have a representative sample of 10 students at a University of California campus. And we want to know the number of them who are transfer students, knowing that from this population, 30% of UC students are transfers. So 30% of UC students came from a community college or another college or higher education institution. So in other words, X has the binomial distribution with n equals 10 and p equals 0.30. Okay, so remember this is n and this is p. So 10 trials, each student is their own Bernoulli trial, where they are either, so the Bernoulli trial itself is they're either transfer or not. So this is what we're going to call our success, and the not being a transfer is going to be the failure. Again, not moralistic. We're just saying that's the group of students that we're interested in within our sample. So let's start with a few questions. What does the distribution look like? Now, it will take some time, if you're doing this by hand, to determine this graph. So you have to take my word for it a little bit, or you can use technology. Specifically, I have here in front of me, though, I do have the graph, so I'm actually going to fill it out myself. And then you'll be able to see the specific outcomes here. So remember that our support is all the whole numbers between 0 and 10. each one corresponding to the number of students in the sample who are transfer students, okay? Now, as for our vertical scale, that's given by the probabilities of our specific random variable. But what I can tell you is that because the probability is less than 0.5, and this is going to be a distribution that's skewed to the right. So the right tail will be lower because the probability of success is lower. And so you'll see now roughly what this will look like. Now drawing in each bar based on the probabilities of each outcome. And you'll notice that they peak around 3, and then they come back down. And they're actually quite low past a certain point. So I'm not being too precise here, but I can write in the probabilities themselves. So our n is 10, and our probability is 0.30. And so we have, I'll write it for slightly askew. And at a certain point, they just become so low that it's not even worth writing anything lower than zero. Or you might as well just put in 0 because it's the precision. Remember that we always try to go to 4 places after the decimal. And then so you'll notice that the probability that 10 people in our sample of UC students being transfer students, given that this is a representative sample, is so low that we might as well call that 0. So now we can understand some characteristics about this. So like we mentioned, this is right skewed. The mode is 3. So the highest probability here is finding 3 out of 10 students. Notice that makes sense because n times p is 3. And we can then use this to find other probabilities, such as what's the probability that we find exactly 2 students who are transfer students in our sample. Now we have the answer in front of us from the graph, but if we were calculating that directly, then we would be calculating from 10, choose 2, the probability of success is 30, raise that to the second power. Probability of failure is 0.70, raise that to the 8th power. And as we found in the graph, then this is roughly 0.2335. Now, on the other hand, if we are trying to find the probability of a range of outcomes, so for instance, no more than 5 students in our sample are transfers, then we'd be looking at the probability of the outcome in which none of them have it, or none of them are transfers. One of them is a transfer. 2, 3, 4, and 5. And this will get very, very complicated very quickly, because you'll have to do this calculation every single time using the same formula, and it can get very tedious. So if you have a TI calculator, this is your moment to shine, because you can make quick work of this without having to rely on the physical calculation. What you can use is a function called Binomial CDF, and what it'll ask from you, it's going to ask for the number of trials, it's going to ask for the probability of success, and it's going to ask for the highest support value, which is X, right? It's going to say that it's going to represent that as X, and importantly, it specifically calculates the first outcome probability plus the second outcome probability plus the third, and so on until it reaches the highest support value. So it's always adding up. We'll talk about this briefly later, but CDF stands for Cumulative Distribution Function. And it works similarly to the way that we calculate cumulative frequency, just we're working with the probabilities now. And it'll make short work of this specific calculation, where it'll find that the probability that no more than 5 students are transfers is actually 0.9527, roughly.